Okay, so my timer started, so I better get going. So thanks for coming. My name's Erin LeDell. I guess I already got a little bit of an intro, so I won't talk any more about myself. But today, what I'm going to talk about is scalable automatic machine learning, and then how to do that inside of the open source platform H2O. So first of all, I don't know how many people in the audience are aware of H2O. It's both a company and the name of the software that we produce. So the company's been around for about 7 years now, and we're in Mountain View, California. And if you're not sure where that is, that's where Google is, and you might have heard of that company before. And then the platform is also called H2O. It's open source. Apache license, which means you can pretty much do whatever you want with it, embed it in any kind of, proprietary application or other business application if you'd like. And we have interfaces in R, Python, Scala, Java. And essentially what it is a machine learning platform that is written from scratch by us, and all of the algorithms are distributed, meaning they can run on multiple machines. And then you can scale them to very large data sets. So this is just a little overview of what I'm going to talk about today. So that URL at the bottom as well, that's where these slides are, if you'd like a copy of the slides. So I'll give you a second if you wanted to take a picture of that. So I'm going to talk a little bit just about what is H2O at the beginning, and then what is automatic machine learning, and then what is H2O AutoML? So that's the name of the algorithm inside of H2O that is automated. And then I'll just end with a few links. Okay, I don't see any more cameras, so we can move to the next slide. Okay, so could I just ask the audience, how many of you have heard of H2O before? Oh, wow, cool. All right, that's good. So I'll just move through these slides fairly quickly then. So this is just an overview. This is a little bit just about what I've already said. So when I mean distributed, that means you can run them on a single machine on multiple cores, or you could run it on a cluster, like if you use Amazon EC2 or something like that. And the algorithms themselves are written in Java, but we know that most data scientists either don't like Java or don't know Java, so we have APIs in R and Python. That's how most people use the platform, but we also have a web interface for people that don't write any code. And then two of the key components that distinguish H2O from other open source machine learning libraries are, one, it's from the beginning meant to be a production enterprise level machine learning library. So we have a mechanism for easily deploying the models to production. So you could export the models as Java code and then compile them into your application. And then if you can remember, if some of you were data scientists or working in the industry back in 2012, that was a year where Hadoop was quite popular. So originally H2O started off as trying to be a machine learning library that would work for Hadoop. And then later on, Spark came along and we extended it to work on Spark. But those are just options. So you could also just use it on your laptop as a normal library. You don't have to use Hadoop or Spark, but it has integration with both of those. And then these are just two terms that I'll introduce you to. This is probably my most technical slide of the whole talk. So there's just two terms that we use in H2O. One is what we call the H2O cluster. That's just what a name for a process where all of the computation is happening. So that's where all of your data lives. That's where all of your models live. That's where your models get trained. And what it is just a Java process. And so the first thing you do when you have a script and you're writing some code to do H2O is you start the H2O cluster. And then we have also a concept called H2O frame. That's essentially just a data frame. And the only thing you need to know about it is that it works like a regular data frame in R or Python. The only difference is that if you're using multiple machines and doing some actual distributed computing, some of the rows will be on one node, some of the rows will be on another node, and that's how we distribute the data. But you don't really have to know anything about it. But it's just our own special data frame platform. So this is just an overview of the library. So Probably the closest thing that you would, if you're not familiar with H2O, recognize is this is something like a scikit-learn if you're a Python person, or if you're an R person, like a caret library, or the newer thing is the tidy models library. So what it is just a unified interface for a bunch of different machine learning algorithms. And some of the things that we do that I think are nice, especially when I go and use some of the other libraries and then come back to H2O, the things that I appreciate the most are things that we do automatically. So if you have missing data, we'll automatically handle that. If you need to normalize your data, we'll do that. If you have categorical data, we'll handle that for you automatically. We also have something called automatic early stopping on all of our algorithms, where it sort of enables you to not overfit automatically. That's usually somewhat of a manual process in other libraries. And then we have everything sort of that goes along with machine learning, like cross-validation, grid search, random search, variable importance, evaluation metrics, and plots. So just basically anything that you would need while you're doing machine learning, we try to stuff that inside the H2O library. Okay, so that's just a very brief overview of what H2O is. So now I'm just going to move on to what is automatic machine learning, and then how many of you have heard that term before? AutoML, anybody? Okay, so there's no real definition of this term. So, and it's also being used commonly now as the name of different products for different cloud vendors are having their own AutoML. So there's a lot of confusion about this term, but I'll just name a few things that I think are, in my opinion, the goals and features of AutoML. So I think one of the goals, when we talk about AutoML, is basically how do you train the best model in the shortest amount of time? And so that could mean two things. One, in terms of how much computation time do you spend, or how much essentially money do you spend to train that model if you're using cloud computing? And then also, we're talking about user time as well, like how much code do you have to write, how long does it take you to prepare that code to be run? So we really just want to reduce the amount of effort that users are taking to get a good model. And that's kind of summarized on the next point as well. But also, when you reduce I guess one of the things about AutoML is the interface to AutoML is supposed to be quite basic. So if you think about what does it look like for a regular machine learning function, maybe you have like a GBM function. It would have all these different hyperparameters, and you have to set them to certain values, and then maybe do a grid search or some other search to get the best values. So with an AutoML interface, essentially what you would have is you want to tell it what your training set is. You want to tell it what your response column is so basically which column are you trying to predict, and then other things would be like how long do you want this to run for, and then maybe you could say which metric do you want to optimize, and that's pretty much it. Like maybe there's other things that you could specify, but when you just have a few things that you can mess around with, there's not much that can go wrong. So that means that somebody who's not super familiar with all the intricacies of different machine learning algorithms could use this function, because all they need to know is what's your data and how long do you want to run it for. So that would reduce the amount of expertise required. And then in general, we hope that we can get better models on average than if you just handed a problem to, let's say, a random data scientist or an average data scientist. We hope that with a machine learning tool or an AutoML tool, you could get a better model. That's certainly not true. There's always probably going to be data scientists who are quite experts, or especially domain experts on the particular data set that they're using, but we, in general, want to do better than just handing it off to an average data scientist. And then another thing that I think is a nice feature of AutoML, and this is, maybe not the intention of AutoML, but one thing I think is nice is it can increase reproducibility in scientific studies or in other type of studies. So often when you see a paper of somebody using machine learning, so right now, machine learning is still new in a lot of other fields. So let's say in medicine, for example. So people are writing a paper, and it's like the first time that anyone used machine learning to do a certain thing. and they get, pretty good results, but maybe what they did was just train a default random forest. So, maybe the results are good, but maybe it's not the best that they could have been, and you kind of don't know what is the actual potential of machine learning. So what would be nice to see is when scientists are writing papers is just use an AutoML library, then you'll know that within that process, a bunch of machine learning algorithms have been tried. You could see all the ones that they tried, what the scores were, and then you have a much more comprehensive picture of what's possible with machine learning. And then, if people are using the same AutoML library, then that would also increase reproducibility. So I think that's just a nice feature that you can get with AutoML as well. So here's a couple things that I wouldn't say are aspects necessarily of AutoML, but just machine learning in general. So these are things that you do when you do data science. So one of the first things is that you prepare your data in some way. And that could just be, pulling it from SQL queries and getting it into a tabular format, or it could be things like feature engineering or dimensionality reduction or things like that. So whatever you need to do to shape your data. And then once your data is kind of ready to go, then you would generate a bunch of models. Because generally right now, we can't predict which model is going to be the best without trying a bunch of them. So I actually think that's where AutoML is going to be, like in 5 years from now. We won't actually have to do the computation. We can predict and then save a lot of time. But that's not, that is an aspect of AutoML research right now. But right now, essentially what you have to do is train a bunch of models and then see how they do. And then if your goal is to get the best model possible, that might not be your goal. But in general, a lot of people would like the best model that they could have from their data. Then another thing that you can do at the end is make some ensemble of the models that you have. Maybe all of the models or some subset of the models. But again, that might not be your goal. If your goal is interpretability or the fastest prediction time or something like that, you might not end up doing ensembles. So here's just a little bit more detail about each of these categories. I won't go into a lot of detail just to save time, but for data preprocessing, I've already mentioned some of the basic stuff, like that whole first bullet there, that's stuff that we do in H2O and all the algorithms. Then we could include things like feature selection and feature extraction. But this last point is actually quite important if you have categorical data. So this is something, or I should point out one of these in particular, something called target encoding. So this is a term that you might not have heard before. It also is known by several different names. So it's also called impact encoding. I think like mean target encoding, a couple different names. So if you haven't heard of that, essentially it's just a way, if you have categorical data, to turn it into numeric data in a way that you're not really losing a lot of the information that's stored in categorical data. So this is extremely important if you have categorical features with a lot of categories. So let's say you have the example that I use a lot of times when I give this talk in the US is the zip codes. So basically postal codes. In the US we have like 40,000 different postal codes. I'm not sure how many you have here, but probably quite a few as well. And sometimes people don't know what to do with that type of data. Maybe they just leave it as numbers and kind of just close their eyes and pretend that's okay. Another thing you could do is just map each zip code to an integer, like 1, 2, 3, 4, 5. But then another thing you can do is target encoding, and that will really improve the performance of your models. So this is a popular technique on Kaggle.com, which is the data science competition platform that you might have heard of. So anyway, those are just some things in data preprocessing. For model generation, we can do all sorts of different things. Like the most popular thing would be maybe like a random search or maybe Bayesian hyperparameter optimization. And then for ensembles, there's a couple different types of ensembling techniques. So the one that I like personally the most is called stacking or stacked ensembles. It's also called super learning. It's all the same thing, but basically a way to use machine learning to find out what the best combination of the models is. So you're actually doing like two layers of machine learning. And we all love machine learning, so that's, you know, a great way to solve the problem. There's another technique called ensemble selection, which is more of a greedy approach. Okay, so something that I mentioned before is the term AutoML is a little bit fuzzy, like people don't really have good definitions for it. I mentioned also companies are producing products that they're calling AutoML, including H2O, which I'll admit, although I think we're the first ones to do that. But so anyway, there's a lot of confusion about what is AutoML. So I wrote this blog post, I think about a year ago now. So if you're interested to learn all the different techniques that are covered by AutoML, there's a very different set of techniques in deep learning versus non-deep learning. So I think that's probably the main differentiator. So Google has a product called Google AutoML, and when it first came out, essentially all it was what's called neural architecture search. So that's very different from what we do and what a lot of other AutoML tools do. So it's just kind of important to understand what is underneath that term. So I break down a lot of those ideas in this blog post and point out a bunch of different tools, open source and non-open source tools. So that's just a reference for later. Okay, so in H2O, this is some of the stuff that we have so far. So yeah, so the current version of H2O 3.26, 3.28 is coming out soon. We'll have some new stuff. But in the data preprocessing section, we have just the first bullet here right now covered. The last thing, the target encoding, that's something that we've been working on for a little while. Essentially, I'm not sure which version that's going to come out in, not 3.28, but probably 3.30. Essentially, we'll handle those high cardinality columns in your data. So if you give an AutoML tool a data set, we don't want it to sort of explode or do anything bad. So if you had that postal code column in your data, a lot of tools would just immediately break because they would either try to automatically one-hot encode that, so it would be adding like 40,000 columns to your data, and then that would extremely, you know, if it doesn't break the software, just slow it down so much that it's not usable. So we want to make sure that if you hand any AutoML tool a data set, that it doesn't just die. So that's why we're adding automatic target encoding. Right now, what we do is a random search across all the different algorithms that we have in H2O, and then we individually tune the models. So at the beginning, I mentioned something that we call automatic early stopping. So we want to not overfit our models, and then at the very end, we train a few different stacked ensembles. And basically all of these points are stuff that we're working on to add to H2O. So in the future, there'll be more of these filled in, hopefully. So you might ask, like, why do we choose these particular things to do for our method? So there's a number of different tools out there. There's not that many in the open source ecosystem. There's a few tools. There's one called AutoSK-Learn, which is like an automatic machine learning tool built on scikit-learn. There's one called Teapot, which is also built on scikit-learn. Those are probably the two most popular tools outside of H2O AutoML that people use, but they all have different techniques. So, Teapot, for example, uses genetic algorithms. AutoSK-Learn uses Bayesian optimization and ensemble selection at the end. So we all have a different approach. So why did we choose this one? So one of the reasons is that, well, first of all, I like stacking, so I just wanted to do that. But one of the things about stacking is that when it works well when you have a diverse selection of algorithms in the group. So one way to get diversity in a group is just to sort of randomly generate those models. So that's why those two techniques work well together. So individually, maybe they're not, like if you did stacking with Bayesian optimization, that wouldn't maybe work as well because all the models are more similar to each other. And if you just did random search without the stacking, you know, you might get a good model, but you're not sure. So that's why we try to combine those two things together. And also, these are things that we already had inside of H2O, so this is just what we do to start out. So this is just a basic overview. I've probably said all of this stuff already, but this is just to summarize. So, oh, and that's the sticker is to remind me to tell you that I have stickers. I forgot to bring them down here, but they're in my hotel room. So if you want to find me later, I have a whole bag of stickers. So that's the H2O AutoML sticker. So we have basic data pre-processing right now. We're adding some more stuff later. We're training random grids of all of the different supervised machine learning algorithms that we have in H2O. I shouldn't say all of them, but most of them. And then we individually tune the models, and then we form two different stacked ensembles at the end. This will probably change over time as well. We might have different additional ensembles, but right now what we have is one that just has all the models in it, and that's usually the best model. It's just a stacked ensemble with everything in it. However, if you're running AutoML for, let's say you run it for 1,000 models, then you have a 1,000 model ensemble, which is fine in a lot of cases. But if your concern is productionizing these models and what is the prediction speed of the model, well, with an ensemble, before you can have a prediction from the ensemble, first you need predictions from all the individual models inside, and then you feed that into the what we call meta-learning algorithm, and then that gives you the final prediction. So if you're, if you can find some way to parallelize that first part, then it could be quite fast, but in general, you probably don't want to productionize an ensemble with 1,000 models in it. So we have another ensemble that we call the best of family, which is essentially just, one from each category. So we have the best GBM, the best random forest, the best XGBoost model, the best GLM, etc. And then I'm just quickly going to show you what does the code look like. So this is for Python. So we import the library, we start the H2O cluster, we load some data. You can load data from not any data source, but pretty much a lot of different formats, but this is just the most simple example, a CSV file. And then we specify how long do we want this to run for. So you can, with H2O AutoML, you can say the amount of time you want it to run or the number of models. So whichever makes more sense in your case. And then you just point it to the data, and then what you get back is something called a leaderboard, which I'll show you in a minute. But quickly, this is just the R version of that, so this is how you do that in R. All right, I see a few cameras, so I'll just wait a second. This is the web interface, so you can see actually more of the options exposed here, so there's a couple other things that I haven't talked about, but I won't have time. So this is if you don't want to write any code, you just upload your data set, press a button, and you have a bunch of models. And this is quite hard to read, probably the numbers on here and the letters, but this is what we call a leaderboard. And so what you get is just all the models that have been trained during the AutoML process, and then sorted by some metrics. So by default, for binary classification, we would sort by AUC, so that's cross-validated, or by default, 5-fold cross-validated AUC. And we see in this particular example, the stacked ensemble all models model is winning, then the best of family is next, then you've got a few XGBoost models. So in H2O, we actually include XGBoost, so you might have heard of that software. So that's right now the only algorithm that's outside of the H2O ecosystem that we bundle in with H2O, but it's a very good library, so we just put it in there. Yeah, I'm not going to spend too much more time. You can kind of look at this in more detail later if you download the slides, but there's some H2O GBMs and then some random forests, a few deep learning models, and then the GLM is at the bottom. So, okay, so I think we're going to do some questions now.
Plenty.
Okay.
Or maybe you wanted to finish first. Maybe.
Oh, that's okay. There are some extra slides, but they
no,
can...
I mean, if you can go in a couple of minutes, because we have like almost 10 questions here.
Okay, I'll just click very quickly through the last couple slides. But better to just download the slides and have more time to absorb. One thing I just wanted to point out is how does this work on something like Kaggle? So have we really solved machine learning? Some people often we get the question like, are you trying to take away my job? No, I don't think so. So essentially, AutoML tools work well in a very short time period. So there was a one-day Kaggle competition. Kaggle does something called Kaggle Days where they do a basically 8-hour competition. In that short time frame, the AutoML tools dominated the leaderboard. And this is where I used H2O AutoML. I didn't do anything. I just pressed a button, ran it for 2 hours, 100 minutes, and scored 8th on the leaderboard. And there's a couple other AutoML tools up there, including one called Driverless AI, which is also an AutoML tool by H2O. And then, but if you have a longer time, so let's say 2 months, like a normal Kaggle competition, usually humans can figure out all different creative ways to reshape the data, to do feature engineering, to beat AutoML tools. So right now, that's the status. You're not going to win all the money on Kaggle by pressing a button yet. So yeah, and then I'll just point you, if you want to see how the different open source tools do against each other, there's a paper that we published in ICML conference this year that is a framework for benchmarking AutoML systems. And I'll just click through to the end. There's also, if you don't want to read the paper, there's a video of somebody reading the paper to you. Kaggle has a reading group, and so they read this paper in 1 hour, so that's good. And then here's just some links. And I think, yeah, we could do some questions.
Well, you answered the first question about the Kaggle competition, so let's go to the second one.
Okay.
What are this one I liked really. What are the benefits of using sparkling water instead of the Spark ML library?
Okay, so so sparkling water is the name of the Spark package, which you can use H2O through. And the question is, how does H2O basically compare to the built-in Spark ML lib? I think they call it Spark ML now. Well, so I haven't done any benchmarks in a few years now, but basically back when we did start to do a lot of benchmarks, just the algorithms are, I don't want to say they're better, but they were better. So I don't know how else to, performance-wise, I think that they haven't put a lot of effort into developing the machine learning portion of Spark as much as they could. They could certainly spend more time and do that, but you have to benchmark it yourself on your own particular data set to know for sure which one would be better, but yeah.
Okay, does H2O support GPU-oriented applications of DNNs?
So there's kind of two questions in there, one about GPUs and one about DNNs. So H2O itself is mostly a CPU-based platform. So I mentioned we support XGBoost through H2O, and that actually can be run on GPUs. So that is the one algorithm inside of H2O that can be run on GPUs. We have another, I mentioned, tool called Driverless AI, which is not open source, which does run on GPUs. And then for deep learning, we have a very, I would say, simple implementation or offering for deep learning. So it's just a fully connected multi-layer neural network that runs on CPUs, but it is quite fast on CPUs. But if you have, let's say, image data or some more complex data, you definitely want to use something like PyTorch or TensorFlow.
Okay, just one final question. How do you see future of data scientist work, having in mind that artificial intelligence platforms take over their main activities?
Well, I think just the model training process itself is quite easy to automate. So I think you'll just spend far less time doing that. Just similar to before we had things like scikit-learn, like you would spend a lot of time combining different random software together to get it all to work. And so then when we had new things like scikit-learn or H2O, it made your life much easier. And so you could concentrate on other things like model tuning, et cetera. That's kind of, now we're doing another leap where you can not concentrate so much on model tuning, but maybe more creative things like data engineering and productionizing, visualization, summarization, that type of thing.
Thank you, Erin. I present you with a certificate for this talk.
Thank you.
And I suppose because we have a number of questions left for you here, I believe you'll be quite popular in the halls, and many people will stop you to ask you about those things that we didn't have time to answer here.
Okay.
Thank you. Thank you very much for
Thank
this.
you very much.